thank the organizer for giving me an opportunity to speak here. So I suppose I have to explain the title and the picture here. So this melting AdS ice into some flatland means so you can actually melt the AdS and making it into flat space-time. So I put the here melting because that in order to be into the flat space-time region inside AdS, you need to increase the energy of the modes of the process. So that's why I put the melting. So I will talk about the recent papers that I wrote. So these two papers. So the first part I will talk about this AdS correction to the fuzzy pool state. And I also will comment on some of the future works. And the second part I will talk about this thing. So the motivation for this fuzzy pool dressing, so is that we know that scattering amplitude with a finite number of photons or gravitons in 4 space-time dimensions actually vanishes due to infrared divergences. So we know since Weinberg that infrared divergences actually exponentiate. And so at the level of individual diagrams, so the diagrams are divergent. And if you resum all the diagrams, then this exponentiate the divergence and it will become vanish. So this infrared divergence comes from the so low energy photon exchange between the external legs in the loops. So the resolution to this problem is actually, if you, so there is a resolution at the level of cross section. If you consider some inclusive cross section where one can actually trace over the unobservable soft quanta, but there is an alternative at the level of the S matrix or the scattering amplitude. So this prescription was actually by Fadib and Kulis and Chang and Kibble. So their idea is that instead of doing the we actually compute the S matrix in some Fock state basis. So instead of doing that, we have to trace the state. So the idea is that so electromagnetic interactions, long range interactions. So the coherent clouds of soft photons or gravitons are already present. So that's why this thing, and this tracing actually gives some infrared finite S matrix. So what I have constructed is that the Faddy-Pulis trace state and AdS corrections to it, and I will follow the Wilson line tracing as a guiding principle to derive it. So we know that in the AdS actually the radius of AdS acts as an infrared regulator. So if you take the flat limit and the asymptotic dynamics of the field, if you do not study appropriately, then infrared divergence will show up. So this is the setup. So the flat spacetime region is inside the center of AdS spacetime region, and we define the scattering states in the flat spacetime region. And this in the AdS corrected Faddy-Pulis dressing will actually cancel the infrared divergences coming from the AdS corrected S matrix. So here this is the picture. So this Sherlock Holmes lens is basically the zoomed in limit. So the flat space-time region is inside AdS, and if you focus around the center of AdS and you do this coordinate replacement, then the metric will turn itself into the flat space-time metric. So this person is living inside AdS. So the idea is that if the person has access to the length scale below the AdS radius, then he cannot probe that he is actually inside some bigger AdS spacetime. So he will just see the flat tiling. So the point here is that the flat spacetime is already in the AdS spacetime, and we know that AdS is dual to CFT. So CFT also encode the physics of flat spacetime in one higher dimension. So this is the general idea of the flat limit. So in terms of these observables, so in AdS, we know that there are boundary observables. So yesterday we also saw some talk that we can compute Witten diagrams. And so AdS, actually the observable is some conformal correlators. So this we can actually insert the operators in the boundary. And in flat space, the observable, the asymptotic construction of the observable is in terms of S matrix. So S matrix, some overlap of the scattering states. So in order to go from AdS picture to the flat space-time picture, we should understand very well that how you can construct the scattering state in terms of these operators. So there are different prescriptions to do this. So there are Mellin space approach and momentum space or position space. So I have listed a few references here. So I'll focus on this position space approach. So the idea here is that so scattering region is inside the center of AdS, And we know that so we can construct some bulk operator inside AdS in terms of this boundary CFT. This is the free field of vanilla bulk operator reconstruction method. And after you are done with this, then we can extract the creation annihilation operators by some Fourier transform. And finally, we can extract the modes by taking the large radius of AdS limit. So, so this is the, after doing this mathematical operation, the kind of results we get. This is for scalar, massless, and massive fields. So the massless particles, actually, there is a smearing of a global time, and there is an exponential with some conformal operator at the boundary. So we can see that, so this, when you take the larger limit, then the exponential will become oscillatory, and the dominant contribution of this integral will come from when tau equals to pi by 2. And for massive case also, the tau has some imaginary piece as well. So this you can also understand in terms of this propagation of particles. So the massless particle actually follows some null geodesy and hit the boundary at pi by 2. And the massive particle never hit the boundary because it follows the time-lag geodesy, or in other words, it can hit the boundary at some imaginary time, imaginary global time. So this picture is kind of a way to regard the flat space holographically. So you can see that this orange fringe region here, pi by 2 and minus pi by 2, is kind of null boundary, and this Euclidean peel set region are kind of future or past infinity. So so now to construct this fuzzy Pulis racing, so as I mentioned in the previous slide that I followed the Wilson line racing prescription. So this Wilson line is basically exponential of IQ times, so U1 gauge field times some line elements, and you integrate. So here there is a magenta and some cyan Wilson line. So this is bulk to boundary Wilson line. So you trace the AdS scalar field with some Wilson line, and there is a CFT representation of this Wilson line as well. So the roadmap is basically, there's an equivalence between this fuzzy Pulis racing and Wilson line racing. And I have actually expressed in terms of this mixed as well as CFT representation. And finally, you can actually extract the modes and you can actually correct actually. So as I have mentioned that there is a mapping between massless and massive particles, or the creation annihilation modes. So you can do it for photons or gravitons, so as well, and you can actually correct it. And that's the thing. So just here's the, so now I will briefly mention that the other work that I am going to present. So this, this celestial amplitude is, so there is a alternative basis actually, which is the boost eigenstate basis, where one can compute the S matrix. So this, in this basis, this free field transform has some conformal primaries, and we can actually compute it. So I choose this problem because in 2D there are a lot of integrable models, and for massive particle, actually there has not been any computation of the celestial amplitude because there are technical difficulties. But for 2D, there are technical simplifications. So this celestial amplitude going from the momentum eigenstate to a boost eigenstate, this is implemented by some Fourier transformation. So here this theta is the rapidity. So if we express the S matrix in terms of rapidity, then it's just the Fourier transformation, and omega here is the eigenvalues of the boosts. So what I have done that there are lots of integrable models, just as sine hyperbolic Gordon model. This is a completely solvable model. So you can see that multi-particle S matrix factorizes. So what I have done that for this model, I have expanded this S matrix into perturbatively, and I calculate the celestial amplitude. So note that here there is a pole at theta equals to 0. So for that you have to do the computation in a subtle way. So that's why there is epsilon prescription, and there are two retarded and advanced celestial amplitudes. So this is the answers of this retarded, perturbative, retarded, and advanced. So you can see here that in all the places there's e to the power pi omega factors, e to the power minus pi omega here and there. So you can understand it from some crossing conditions, so which S matrix also obeys. So in the celestial space, this crossing condition is basically this. So if you are some finite temperature quantum field theorist, just like Loga here at ICTS, so you can think that this equation is kind of some KMS equations, and this omega is some Rindler energy or something. So there are also unitarity constraint. So I have also imposed the real analyticity condition, and this translates into this thing. So to solve this unitarity constraint and to satisfy it, you have to do the in subtle way. So you have this retarded with some advanced and convolution of that. If you do not do this, then if you will get some divergences.
Sarthak, you have 2 minutes.
Yeah. So here this, if you perturbatively write this in terms of this Fn, so we can see that we can actually bootstrap the amplitude. So there is an ambiguity here. So this term is basically the difference between the retarded and advanced celestial amplitude, which is the which can be given by the pole at theta equals to 0, as you can see from the I epsilon prescription. So this term is fixed by crossing and unitarity, and this is not. So I just mentioned some wish lists and work in progress. So in the first part, I mentioned that the Faddeev pool is dressing. So this I have constructed in with the Wilson line dressing. So there are alternative prescription actually in the literature of flat space. So where the thing is that the S matrix amplitude that conserve asymptotic charges are finite. So like there are some literature also in AdS that for leaky boundary conditions, but we do not know how to construct this thing from non-leaky AdS. So also there are some other works that the AdS correction to the short photon or graviton theorem. So how the infrared divergences will show up when we take the flat limit. And I also mentioned the celestial amplitude story and flat limit of AdS4 CFT3. So one can try to combine these two mapping and understand something. So there is some understanding at the level of 2-point function, but I am doing some work on this direction also. And there are celestial amplitude for 2D integrable theories. Also, I have some understanding that how one can compute the tree level diagrams and how to take the flat limit of it and map it to some celestial amplitudes. But there are general questions that in integrability is the integrability notion in general true? Means can we solve this integrable models like sin H Gordon in AdS or in d sitter also? Because we do not know this, but this is an interesting question to ask. So that's all I have to say.